In this recording, I'm going to tell you what I know about lead water pipes. They are a problem, as you're probably aware. They're present in older homes, so any houses built, before 1960s may have a lead water pipe connecting the house to the mains pipe in the street. If you want to know why lead was used, well, you only have to look at a pipe. The lead pipe you can bend really easily. So if you imagine you're building a house, you wanted to put a pipe down, you needed to lay it to the mains pipe. It's quite convenient to bend that pipe. So lead was a really good material to use. It was very bendy. This was in the days, maybe 100 years ago, you didn't have plastic. Also, lead, believe it or not, it doesn't corrode very well. So it's corrosion resistant, and this is the reason why lead pipes still remain from old antiquity sites like Roman baths and so forth. If you go down to the place of Bath, you'll still see Roman pipes there in the old baths, and that's because they're there because they corrode very, very slowly. So it's in many ways it's an ideal material. Low corrosivity, bendy, you can easily plumb it onto other pipes. But the problem is obviously that lead is toxic and isn't good for health. And people have known about this for a long, long time. So if you go back to even the Roman times, there's a writer in Roman times called Pliny. He wrote about things like the volcanoes of Pompeii, but he also wrote about lead. And it was well known in those days that if you drunk alcohol or wine from lead containers, that it didn't make you very well and would make you quite mad actually. And even in the Roman times, it was good. People put wine into leaded goblets because something called lead acetate formed, which actually makes things very sweet, and so it made the wine taste nice. But it was known then that it wasn't good. Even so, when water started being piped to houses, maybe 150 years ago, they used lead as a material because it was readily available. It was cheap to make. It's easy to extract lead from rocks because lead has a low melting point. So it was very convenient, and people chose to disregard the health effects of lead. But if you think about it, this is 150 years ago. There were lots of other health problems in those times, and maybe lead was a low priority. But we've got this legacy, and the legacy is particularly in former industrial areas like the north, like Huddersfield, for example. So if you go around Huddersfield, you'll see lots of terraces. I live in a terrace. It's over 100 years old, and the terrace is housed on one side, housed on the other side, and ours contained until very recently a lead water pipe. Not in the home. These were stripped out a long time ago. There's copper pipes in our house, but the lead is between the house and the mains pipe in the street. And in our case, the pipe was 10 metres long. In some properties, bigger properties for example, they have much longer lengths of pipe because they've got bigger houses, bigger gardens, maybe the kitchen is at the back. There's quite a long length of lead pipe. Most customers don't know they've got lead pipe or would rather not think about it. Water companies, it is an issue for water companies, and the reason is that there are legal limits for how much lead can be in your tap water. Now, water companies, they don't own all this lead pipe. Most of the lead pipe is owned by the customer. So if you've ever come out of your house where you live, if you go to the pavement in the street, you may well see a square box in the pavement, and it might have YW on it. But if you use a special key, you can open the top of that box, and inside is a tap, and it's called the stop tap. And on one side of the stop tap to the house, that's owned by the customer, but on the other side, the stop tap to the mains pipe, which is probably quite close, maybe a metre away, that's owned by Yorkshire Water. But most of the lead pipe is owned by the customer. So there's nothing that Yorkshire Water can do because they don't own the pipe, but they are responsible for the amount of lead in tap water. So you might think, well, what can they do? They don't own the pipe. How can they control lead? And what are they doing to tap water? Well, it turns out that people started getting concerned about lead in tap water maybe in the 1980s is really when they started getting concerned. It was a time when people were thinking about changing from leaded petrol to non-leaded petrol. They wanted to find ways of reducing intake of lead. So they looked at tap water and they discovered that, well, tap waters, there's different types. So you've probably heard of hard water, there's soft water, and they respond to lead in different ways. So people did this research and they looked at it and they said, oh, look, this is a soft water, it's got this pH, it's giving this amount of lead levels, whereas in this area, when we sample from our customers, it's got this pH of water and this type of hardness, so it gives this level of lead levels. So when they did these studies, they soon came to realise that there was a relationship between the water quality and the lead levels. And when we say water quality, most of the time we're actually meaning chemical composition. So it doesn't mean how safe it is to drink or anything, but most of the time it means composition. So the water composition, the most important parameters for lead in tap water are pH, and there's another important parameter, and it's called alkalinity. Now, alkalinity is something you may not have heard of before, but it's essentially how much hydrogen carbonate is in the tap water. And as a general rule, the higher the hardness, which in hardness is to do with how much calcium is in the water, the higher the alkalinity. And depending on where you live, your tap water will have a different alkalinity. So for example, if you live in an area, a lowland area, where water, and you take your water from a river, then the water will have fallen down as rain and it will have seeped through the ground, through the soils, and there it picks up lots of calcium and lots of hydrogen carbonate because it will react with the rocks in the soil. And so river water, lowland river water, tends to have higher alkalinity. Whereas another type of water, let's say an upland reservoir, so around Huddersfield, rain falls and it quickly gets into an upland reservoir. It doesn't pass through the rocks and soil very easily, so it doesn't pick up lots of hydrogen carbonate and calcium, so therefore it tends to be softer water. So there's two types where we talk about one river water, we talk about upland water. There's another one as well. So you can get water from boreholes, so you can literally, it's like a well that you bore a hole into the ground and then water comes into it and you extract the water. And people also get, there's a lot of water actually comes from boreholes too. And not so much in Yorkshire, but in other areas there are boreholes. And borehole, a bit like river, it'll be in through the soil, so it picks up quite a lot of hydrogen carbonate and it'll have what's relatively high alkalinity. So pH is important and alkalinity is important. And as a general rule, well, you could say in tap waters of lower pH will give rise to higher lead, and you might think, oh, that makes sense. But actually it's more complicated than you can't really just make that assessment straight away. But anyway, water quality is important. So let's what I wanted to do is move away from water quality now and then talk a little bit about what happens in a lead pipe. So lead pipe is made out of lead metal. The pipes, some pipes maybe are a 1/4 inch in diameter. Water passes through them, and as the water passes through them, what happens is that lead is oxidized. So lead metal, this is a corrosion process, if you like, because lead is oxidized to lead metal, and the thing that's oxidizing the lead 2 plus ions is oxygen. So there's plenty of oxygen in tap water, and the oxygen acts as the oxidizer. So lead metal becomes lead 2 plus, and oxygen is itself, because it acts as the oxidizer, it's reduced, and it's reduced to water, or depending on the pH, it's reduced to hydroxide ions. So you have this oxidation reduction process taking place on the surface of the pipe. So obviously corrosion rate is important for lead pipes, but something else happens as well. So as the lead 2 plus ions are released, they react with anions in the water. So for example, there's carbonate in the tap water. As I said, it can be as hydrogen carbonate, but lead carbonates are insoluble. So when the lead 2 plus ion comes off the surface of the pipe and it's oxidized, comes off into solution, it quickly meets a carbonate ion or hydrogen carbonate. The hydrogen ion comes off and you've got lead carbonate, and it forms a lead carbonate. Now there's different lead carbonates, it's complicated. So there's one called cerussite and there's one called hydrocerussite. Cerussite is PbCO3 and hydrocerussite has got a carbonate in, but it's also got a hydroxide in as well. And they're two different minerals and they have slightly different solubilities, and one is preferred to the other depending on the alkalinity and the pH. So water is passing through, the lead is being corroded and oxidized, and lead carbonates are forming. But the lead carbonates, they can form in the tap water that's passing through straight through, but these are crystals that are growing, and crystals like to grow on surfaces. So what happens is that the lead carbonate prefers to grow directly on the pipe rather than in the solution. So you end up with the lead coming off, reacting with the carbonates, and then coming out of solution, but growing, the lead carbonate that's insoluble grows on the walls of the pipe. So you end up with a pipe that starts to have a mineral layer. And so you've got this lead pipe with this inner mineral layer of lead carbonates. Now what we find is that there's a mixture. This lead pipe has a mixture of the two or more types of carbonate. So some cerussites on it, hydrocerussites on it. We don't really know how they relate to each other, and that's one of the bits of work that I'm doing. Is I'm trying to do microscopy to look at where the cerussite and hydrocerussite is. So until about 20 years ago, that's what happened. And then, as I said, people started to get concerned about lead levels. So, and they thought, oh well, we've noticed that cerussite and hydrocerussite are on these pipes or these carbonates. These are insoluble. What happens if we grow an even more insoluble layer on our lead pipe? Wouldn't that, therefore, reduce the amount of lead in tap water? So they scratched their heads and they came up with phosphate. And they found that lead phosphates are more insoluble than lead carbonates. So work was done, and it was discovered that if you added 1 milligram per litre of phosphate to the tap water, that was sufficient to bring down lead levels significantly, and it has. So now what you see is, in the past, lead levels maybe 20 years ago used to be routinely 50 parts per million to 100 parts per million. They're now less than, a majority of them are less than 10 parts per million when you measure them. So it's been a significant reduction, and it's all because of adding phosphate to the tap water. When you add phosphate, there's a number of different, just like the carbonates, there's a number of different lead phosphates, but the most insoluble lead phosphates are the ones which are called apatites, and they are lead phosphate hydroxide, which is actually called hydroxyl apatite, and lead phosphate chloride, which is called pyromorphite. Sorry, the other one was hydroxyl pyromorphite, sorry, and the one with the chloride in is pyromorphite, and they're very insoluble. And because they're very insoluble, no one's actually observed them directly, but we're assuming that they form on the insides of lead water pipes. So water companies, who in the UK are called water utilities, they add phosphate, and it's done across the whole of the UK. They're all adding phosphate, and they're mostly about 1 parts per million. Sometimes the phosphate dosing, which takes place at the water treatment works, doesn't work. So maybe the dosing pump is broken. So sometimes it's not always phosphate getting through, but the majority of times it's phosphate getting through. So coming back, you've got a number of processes taking place on the lead pipe. You have corrosion taking place, and you also have mineralization taking place on that pipe. And really all the projects I've got are all to do with trying to understand what's going on the surface of the lead pipe, whether it's to do with corrosion, and so far I've done very little on the actual corrosion process. Most of the work I've done has been on the mineral side and the solubility side. So some of my projects are to do with the corrosion on the lead pipes and some of the mineralization. Now, With regard to mineralization, I've talked about pyromorphites, hydroxyl pyromorphites, those are lead phosphates, and I've talked about cerussite, hydrocerussite, they're the carbonates. Um, there are quite likely to be other minerals there too, and you can identify the minerals, and there's two techniques I generally use to identify minerals on pipes, and one is FTIR, which you've all done lots of times before, and you might think, oh, FTIR is just for organics, and it is a really useful technique for organics because it does covalent bonds. But it's also good for minerals as well, because if you think about it, a lead carbonate, well, that's got covalent bonds in it because it's got the carbonate, so it's carbon-oxygen bonds. And so FTIR is really good as an identification tool. You can tell what groups are, whether it's phosphate or carbonate in them. The other one that I tend to use is powder X-ray diffraction. And powder X-ray diffraction is also really useful because the minerals that we grow are crystalline. And because they're crystalline, they've got repeat units inside them, and they undergo something called diffraction. And if you do diffraction and shine X-rays at them, the X-rays split into and diffract, and you get little spots. And our machine that we've got identifies the positions of the diffracted spots, and these positions, they tell you something about the spacings of the layers within the crystal. And it gives you a pattern, which is a spectra, which we can use to identify. So we can, with the identification, you can say, oh, this is cerussite, this is hydrocerussite. But you can also say, oh, the lattice has changed slightly. It's grown slightly bigger in one axis than the other. And you can demonstrate a change. So the two main things we do use are FTIR and XRD. There are others, it's just these are the ones that we've got available. So I've talked really about why it's a problem. I've talked about some of the chemistry. The chemistry is quite complicated, so I'll just return to it for one moment. This is regard to corrosion. I've said lead oxidizes or corrodes and becomes lead 2+. Well, actually, it doesn't, but there's something else going on too, because when I look at lead pipes and I take a cross-section through them, so if you take a piece of lead pipe, cut a piece, mount it in resin and polish it, you can look at the layers on that corrosion layer. And what you see is you've got lead metal, and then next to the lead metal is a lead oxide layer, and it's usually bright orange, and then it's followed by this other layer, which is the carbonate or the phosphate layer. But there is this lead oxide. So when you're dealing with corrosion, we're not quite clear of the mechanism, because it's not lead going to lead 2+ and the lead 2+ mineralizes. It looks a bit like lead is transforming into lead oxide, so there's still an oxidation reaction, but it's transforming to lead oxide first, and then it goes to the carbonates and the phosphates. The slightly weird thing about it, which you don't yet know, is that the oxide should be quite soluble. So in a way it should sort of disappear, but it doesn't. So there's something going on there. So the last thing I want to say is, what have I been doing with lead pipes? Well, the main thing that I've been doing is I've been looking at lead pipes from a structural point of view. So we're trying to work out what's going on in the mineral layer. So trying to characterize it, trying to say what's there. We've also been trying to grow the minerals that we identify on the lead water pipes. So if you want to do some studies on those minerals, it's hard you could scrape the minerals off the lead pipe, but you end up, the scrapings are a mixture of lots of different minerals of lots of different sizes, and it's hard to know what's what. But if you identify, for example, that cerussite is there, then separately you can go and grow cerussite in the laboratory, and then you can do some sort of chemistry on that lead cerussite, and then make inferences on what the chemistry going on in the lead water pipe. So solubilities we're very interested in, for example. So growing minerals, but just one particular type of mineral, measuring their solubility gives us some information about what might be going on in the pipe. So that my focus has been on characterizing the pipe and then looking at those minerals and perhaps identifying some of those minerals. So I hope I've given you some insight into there. One of the things that we know that lead is dangerous and toxic, but I until now I haven't done much on the biology side of lead. I've stuck more to the problems, the water problem, the problem for the water utilities of how to understand their lead levels. So why is it that one area, maybe let's say Leeds, one area of Leeds has very low lead levels and another area of Leeds maybe has quite higher lead levels? And as a water company, you want to take those higher lead levels and bring them down, but you don't know how. So really that's my focus, is how to enable water companies to make some changes, whether even just a change in pH or maybe changing the amount of phosphate, so that they bring those lead levels down. Ultimately, the best thing to reduce lead levels in tap water is to remove the lead pipes. And I've done that in my property recently, but it's expensive. I would say though, it's not as expensive as buying a house. So typically, it will cost anywhere between £400 and £800 to exchange a lead pipe that runs between your house and the garden. And the government could legislate, but it doesn't want to add extra costs onto consumers. So although in actual fact lead in tap water isn't great, but you could take the lead pipes out. So you could have a scheme of removing all lead pipes. But actually, if you think of each property, let's say for the property owner, it costs about £400 to £800. For the water utility to remove their bit, it costs about £800. So you're talking of maybe over £1,500 per leaded property. So if you add that up across a whole region, let's say for Yorkshire Water, for example, that turns out into millions and millions of pounds. So there's a reluctance to go down that road. The reluctance, also a reluctance, because it's not just, believe it or not, it's not just the lead pipe that gives off lead. So in copper water systems, there's some things can happen. First of all, that the copper pipes, when they're joined to each other, there are different types of joins that you can use, and commonly you can use a special coupling joint where you just push two pipes together and they come together, or you can use solder. Now plumbers are all meant to use lead-free solder. However, lead-free solder looks like lead solder, or rather so all solder looks like solder. So as a customer, you wouldn't know the difference between a leaded solder and unleaded solder. Now, most plumbers, I'm sure, are very honest, but some plumbers, I'm sure, if one's cheaper than the other, and in the past it certainly has been the case that the leaded one is cheaper, then they've carried on plumbing in your house using the lead solder. So just because you don't have a lead pipe, you may have lead solder in your home connecting the pipes. And you may think, oh, there's not much lead there, is there? Because most of the pipe is copper, there's a little bit of solder. But the problem with lead when it connects to copper is they have different electrochemical potentials. And when lead comes in contact with copper and you've got water thrown through a pipe, then you have what's called a galvanic cell. So it's equivalent to, when you do a practical and you've got copper against zinc and there's a cell starts, you've got a voltage and things start happening. But the same happens with lead and lead solder with copper pipes. So you can have quite a high amount of corrosion taking place. So even if you got rid of the lead water pipes, you may still have problems because of the solder. Then it's not even just the solder, but brass, which is often used to help couple pipes together, or brasses in the units in the kitchen tap. Well, actually, brass has tiny bits of lead in it too, believe it or not. The lead is added because it gives the material, the brass, properties which make it good to use in a tap. But nevertheless, lead is there. So there's lots of little places where lead can get into the tap water. So it's not just about lead water pipes. So it seems that for the foreseeable future, water companies will be treating their pipes by modifying pH and alkalinity maybe, and by adding phosphate so as to keep lead levels low. But they would like to have a much better understanding on what's going on, and they'd like to have a much better control. There's lots more I can tell you, but I think that's sufficient at the moment. When I want you to do the literature reviews, really what I want you to do is you need to find out some references to do with lead and lead in tap water. I think that's quite important. I will look for some references for you, so I'm going to send you all out some, but you need to find some yourself. There is plenty. It's lead in tap water. Write up a bit to do with the field, and then you want to sort of concentrate a little bit on the area you're focusing on. So, for example, if you focus on corrosion, then you need to talk a little bit about what happens in corrosion, just generally, just general corrosion, not just lead corrosion. Because one of the problems with the literature review at this point is that you don't know much about the subject area yet, because you haven't done it, you haven't been into the lab yet, but you'll know a lot more by the time you do your report. So it's hard to do a literature review really, but if you're doing corrosion, focus a little bit on general corrosion too. If you're doing grey minerals, then you need to talk about the lead in tap water, but then you need to look at minerals, and you need to talk about find out a little bit about who's done what before in growing those minerals. You might even want to say a little bit about the minerals that are found on lead water pipes, so things like the mineral layer, the hydrocericides and the cericides, because there is material out there for you. And if you're doing a project which looks at zeta potentials, which one of them is, and you're looking at pyromorphites, then again you need to say something about the mineral layer, how the lead pipes, the chemistry of lead pipes, why lead is a problem, but then you also want to focus a little bit on charges, on the fact that the particles that are formed are tiny, the crystals are tiny, they're what's called colloidal, they'll have charges on them, so you need to talk a little bit about zeta potentials. And if you have any, finding references to do with zeta potentials and leaded minerals, and maybe you want to talk about them. I hope you find all this useful. I hope you're all going to do really well. I think I've enjoyed all meeting you. Lead is a fascinating problem. Hopefully we're going to go out and I'll show you some lead pipes and stuff like that. We can go out and see a Yorkshire Water guy as well. And maybe we can even fit in a visit to a water treatment works.